In this video, we examine how sensitivity analysis can be used to analyze changes in the objective coefficients as well as the right-hand side of the constraints of a linear program. The video also provides a brief overview of the fundamental insight for linear programs. Let's imagine we have a general linear program in matrix form shown on the left. The corresponding initial simplex tableau is shown on the right. The uppercase I indicates the identity matrix. Below it, the optimal simplex tableau is shown, meaning the tableau in the final iteration of the simplex method. Notice that the coefficients under the original variables in the final tableau are determined only by the original parameters a and c, as well as the coefficients under the slack variables in the final tableau. We refer to the coefficients under the slack variables as the shadow prices, or y star, and we'll discuss those further in a minute. The remaining values of the final tableau of the original variable columns can be determined using the remaining values under the slack variables, also referred to as S star. The right-hand side values can similarly be determined from these values as shown in the tableau. This is what is referred to as the fundamental insight, and is essentially based on the concept that the final tableau is constructed using linear row operations. Hence, it can be determined solely from the initial parameters, as well as the values in the slack columns of the final tableau. Let's say that we weren't sure about some of the original parameters of the problem. B could be B bar, C might instead have the value C bar, and A might actually be A bar. In that case, we could of course simply run the simplex algorithm from the start once more with the new parameters. But we could also take a shortcut and use the fundamental insight to calculate how the new parameters have changed. What was the final tableau before? The new initial tableau is shown on the right. Notice that we haven't changed anything in the slack variable columns. Hence, after the simplex iterations that led to the final tableau before, these columns must hold the same values as before. In other words, y star and s star haven't changed with the update of the parameters. We can fill out the rest of the tableau using the fundamental insight as shown here. What we have done now is essentially to apply the same row operations to the new initial tableau as we did to the old one. In this way, skipping the iterations that we already have done once. However, with the new parameters, this final tableau might actually not be optimal anymore. It might not even be feasible, meaning that we might have to perform a number of primal or dual simplex iterations to reach the new optimal solution. This kind of analysis, called sensitivity analysis, is a simple way of testing how changes in the original parameters change the optimal solution. And it can be very helpful for determining, for example, if a production should increase its capacity in order to increase profit. In the following, we show examples of changes to the objective coefficients as well as the right-hand side of the constraints. Let's start by looking at changes to B. We know from the fundamental insight that changing B will change the optimal solution value as well as the right-hand side of the constraints given by the two relations shown here. Because the right-hand side of the constraints is changed, we might get negative values, meaning that we have to make one or more dual simplex iterations to get back to feasibility. It might also be the case that we change the right-hand side so much that we cannot reach feasibility through dual iterations, in which case the primal problem is infeasible. Let's consider the example linear program shown here. We change B from this to this. The optimal tableau to the original problem is the following. Using the formula shown earlier, we can determine the new tableau given the changes to the parameters. Most of the tableau is the same, but the right-hand side has changed. We calculate the new objective value as well as the new right-hand side of the constraints. Notice that the new tableau is infeasible. Hence, the next step is to make a dual simplex iteration. However, before we do that, it should be mentioned that the calculations used to compute the new right-hand side can be simplified slightly. We define the changes in the parameters as delta B. Now the changes in the right-hand side can be calculated like this. Notice that because we have only changed one of the parameters, we can skip parts of the calculation. The parts of the vectors and matrices that we do not need in the new calculations are marked with dashes. Having now calculated delta C star and delta B star, we can update the right-hand side like this, in which case we reach the same result as with the full calculations used before. Now if we were to perform the necessary dual simplex iteration, we would go from this infeasible tableau to this tableau, which is both feasible and optimal. Notice that the optimal objective value has increased from 32/3 to exactly 12. If we look at the shadow prices of the old solution, we can see that the value associated with x4 is 2/3. If we look at the shadow prices of the old solution, we can see that the slack variable associated with x4 is 2/3. x4 is the slack variable associated with the constraint which right-hand side we have modified in the sensitivity analysis. Looking at the formula for determining the new value of C star, we can see that increasing the right-hand side with 1 unit should increase C star with exactly the shadow price of 2/3. However, this only holds when the basis does not change when the parameters are modified. In the example we just looked at, C star ended up being 12. Even though the shadow price indicates that C star should have been 32/3 plus the shadow price of 2/3 times a change of 3 units, i.e. 38/3. We can determine the interval of change in the right-hand side coefficients for which the basis is unchanged and the shadow price holds. We refer to this interval as the allowable range. The interval is exactly the values of the parameter in question that does not lead to any negative coefficients in the right-hand side of the constraints. In other words, this should hold. As an example, let's determine the allowable range of the parameter we changed before. Using the delta method shown earlier, we can write this. We are using delta as a variable here, and we are only considering changes to the right-hand side of the second constraint. This leaves us with the following 3 inequalities. As long as delta respects these inequalities, the right-hand side will be non-negative and the shadow price of 2/3 will hold. We calculate the allowable range of delta to this. Given that the original value of the parameter was 4, we can now say that the allowable range of the right-hand side of the second constraint is 3/2 to 6. Within this interval, adding 1 unit to the right-hand side will increase the optimal objective value with 2/3, and subtracting 1 unit will decrease it equivalently. We now take a look at changes to the coefficients of the objective function. Changing the objective function works very similarly to changing the right-hand side of the constraints. The simplex tableau is updated using the formulas shown here. We return to the example from earlier and change the second coefficient of the objective function to 3/2. We then update the final tableau using fundamental insight. Notice that only the coefficients in row 0 under the original variables are changed. Since we did not change the A matrix at all, the corresponding A star matrix is also unchanged. Looking at the second column of the updated tableau, we see a 1/2 under x2, where we should have a 0. Since x2 is a basis variable. The tableau is updated with the appropriate row operations to eliminate the 1/2. This involves subtracting a 1/2 times row 2 from row 0. The tableau is now on proper Gaussian form, and since none of the coefficients of row 0 are negative, the solution is optimal with the new parameters. If one of these coefficients were negative, we would have to perform a primal simplex iteration to reach optimality. But because that is not the case, it means that 3/2 is within the allowed range of the objective coefficient of x2. We can calculate the full allowed range of this coefficient. We call the coefficient of x2 in the objective function c2. Let's say that we want to add delta c2 to the value of c2. As just shown in the specific example, that means that we need to do a row operation to bring the tableau to proper Gaussian form. In general, we add delta c times row 2 to row 0. This changes the coefficients of row 0 to this. Now, in order for the tableau to be optimal, all coefficients of row 0 must be non-negative, In this case, that just means that the single equality here has to be respected by delta C2. Hence, the allowable range of parameter C2 is that C2 should be greater than 4/3. This concludes this video.